Our first speaker is Ghulam Rabbani from University of Indian Institute of Technology, Delhi, and the talk that he will give is numerical investigation of behavior of bubbles passing through both Newtonian liquid-liquid interface. Thank you very much. Floor is yours. Please go ahead.
Yeah, first of all, I would like to thanks dear sir and my dear friends that who gave me an opportunity to speak on the topic for my work. And I would also like to thanks for the whole OpenFOAM community who contributed a lot like for this as a student I am like getting help from this. So I'd like to thanks for the whole team of the OpenFOAM community. So I would like to talk here about the bubbles passing through the liquid-liquid interface. So here it is basically a three-phase things. So this is my content in which I would like to have a small discussion over introduction, problem statement, and all the governing equations. How did I set my cases, and then how did I run the case and my post-processing results. So this is the introduction. Like as we see, the bubble have lots of multi applications from metallurgical field to and many other various application it has. Like you can see the picture over here. Like there is a top liquid, there is a bottom liquid, and a bubble inside the bottom liquid. So when the bubble, and this is the interface between the two liquid, so when the bubble interact with the liquid interface, so figure B, figure C, D, E, F, all these are the possible outcomes. Like bubble, it disturbs the interface, like you can see in the figure C. In the figure B, you can see as a thin film is formed that is of heavier liquid only. Just for identification, it shows by red color. And in the figure D, it forms a jet formation in the subpart D. And E, F, all these are possible outcome that depends on the various properties of the fluid, that what fluid we are taking it. So I have taken such a small problem to solve it by an open form. So first, in the open form, I found it there are two solvers present, a multi-phase solver and the interface multi-phase interform and interform solver are present. So in the interform solver, I found it that it is for the two phase. For the incompressible fluid, whatever your case is laminar or turbulent, you can use it interform solver. But when there is a more than two phases, then you have to go for multi-phase interform solver. So advantages which I found in open form is that, like, it is not like a commercial package like ansys and comsol. It requires a license cost. It is a free open source and you can use it. It does not require a license cost. And its flexibility, that in which you can customize your code if you're going deep into the code, and you can customize your code according to the problem. This flexibility this is present in the open form. And it support high performance computing and huge solver database. And the point and the and the although it has its own mesh generation things using block mesh, but it can also you can also import the mesh from the other software too. So this is my problem statement. You can see the picture. The upper part is the lighter fluid, the lower part is the denser fluid, and this is a small air bubble, a yellow color small air bubble. So the two fluids, upper and heavier fluid, the all the datas which are present. This I have taken from a paper. This I have taken from a paper. So slowly so mm, s- mm, so so this is the interfacial tension you can see between the two fluid is 0.0142 newton per meter. So in the multiphase interform solver, it is based on the VF technique, this solver. And you can, these are the governing equation is used for this solver. Like first one is the continuity equation, second is the momentum equation including the surface tension force, because when the bubble is near to the interface, and the interface, all the surface tension things are coming into the picture. So surface tension force are already implemented in this multi-phase interform solver. And the phase transport equation, the equation number 5, that is for phase fraction. Like primary phase, whatever you are taking as an air, then water and oil, all these are like different phases. So one transport equations is implemented in as an equation 5. And but one thing we should keep in mind, for each computational cell, the sum of the phase fraction is unity. And in the equation 7, the surface tension force is proposed by Black Bill as an this equation you can see as a surface tension force. These all things are already implemented in the multi-phase interform solver. So I have taken a base case. How did I set the case? That I will tell you in brief. I have taken a base case under the multi-phase tutorial, dam break 4 phase. So from there I got the start to run this problem, how to run this problem. So first I copy all the folders in my run directory with the name bubble rise folder, whatever I have taken. And although I told that mesh is generated with the both the things, block mesh and any commercial software, I use the commercial software for ICM CFD for generating the mesh, so which I have imported in the OpenFOAM. So first I copied all the folders of zero constant system. All these folders are present in any when you set the case, these are the basic folders which are present. And if you are importing the mesh then from any software, then a mesh file will also come. uh, so this is my meshing which I have done with ICM CFD. With my domain of interest, I have means done a finer grid and finer grid, and we can import this into the open form when everything we have set the case with the command fluent most mesh to form. So in brief, I would like to tell what are the folders present and what is mainly what we have to do in this folder. So in the zero folder, you can see all the phase fraction for the all the phases, and you can see the equation number 5.
Yes, please go ahead. Thank you.
Yes. Yeah, under the zero folder, I have changed the PRGH and U folder, U folder for the giving the boundary conditions. So, like in the PRGH, I have given the fixed flux pressure. Like if you should know that if you are giving one thing as a Dirichlet boundary condition, the other should be Newman boundary condition. Okay, so here in PRGH, I have given left, right, and bottom wall as a Dirichlet Newman boundary condition. So that's why in U you can see directly the left, right, bottom is the Dirichlet boundary condition, and in the upper wall for the PRGH, I have given the Newman boundary condition, and the upper wall for the U I have given the uh, Newman boundary condition for the upper wall inside the U. So for the PRGet, it will be Dirichlet boundary condition. Dirichlet means we are assigning a certain value for it, and Newman there is some law. There is a like gradient, something things will be there. So in the case under the constant folder, under the constant folder, we will just change the surface tension, density, kinematic, viscosity things. And if you are running the laminar case, we'll go for laminar, and if you are using the static mesh, we'll just set the static mesh. And so in the transport properties, you can see the different water, oil, air inside the multi-phase interform solver. Like the kinematic, viscosity, and density, it is fixed like this. Oil, it is fixed like this. We have given specified the value, and ultimately at last the surface tension and interfacial tension between the phases is being set. So in the under the system folder, the FE schemes control dict and set field dict files. These have been changed from the base file of Dambreak 4 phase tutorial, and but FE solution remains the same as Dambreak 4 phase tutorial. So in the FE schemes, like the time temporal discretization is done through Crank Nicholson, and rest there is a change which I have done in the divergence scheme. Rest remain the same. In the divergence scheme, the U and alpha, like you can check it for which the simulation is running smoothly. So I got these two alternative, like Gauss limited linear V1 and Gauss Van Leer. These two are the we are getting actually these all are the enhanced version of the Gauss linear. So for with this we are getting the smooth simulation. And control dict file, under the control dict file, like application, like the solver which we are running, that will give the multi-phase interform solver. And start from, like I've selected the latest time, like once it is your simulation is stopped, then again you restart, it will be started from the latest time. And time step I have set as 0.005, and the it is an adjustable time step. These things I have only changed, and the current number I have changed zero point 0.5. And set field dict, set field dict is the command inside an open form by which you can specify your field inside the computational domain by different transport properties. Like by default, in the first thing, by default field values, the first I have selected the water for the full computational domain, rest everything was 0. And then on specifying the upper phase, like lower phase is water already, and like replacing the upper phase with the oil. We have just in the box to sell command, we have just given oil as one, rest all other 0. So oil is replaced in that portion with the water. And for the bubble we have given sphere to cell, center, radius, and like this specify the dimension. Like I have used the static bubble if I would like to, and if I would like to use the, like with input some velocities over it. So here inside the default field values, wall vector field values present, you can take it as one inside this sphere to cell. Now once my case is set up, then these thing we have to for running the simulation, first we have to in the direct in the run directory, we have to write fluent mesh to form for importing the mesh. And then we have to write the command set fields. You can also do check mesh also before the set fields. And then then you have to do set fields. When you have written the set fields, your domain is specified with that transport properties. And then the solver which you are using, that you write it multi-phase interform, and then your simulation will start. And when you want to visualize your simulation, you can do it, you can do it with paraform. A paraform is a tool which by which you can visualize it. Although other software also, they are like tech plot, which takes the control dict file under the system folder present, to visualize the simulating results and for the post processing things. So these are some are the validation things, like these are some of the validation things that to check the multi-phase interform solver. Like we see that how nicely the multi-phase interform solver capturing at all the time steps, like time step 0.317 second. These are the experimental results. You can see in the nearby time steps, the bubble is at the same positions, almost at the same positions, and the shape of the interface is also the same. And these are all different time steps. You can see with the time when the bubble rising, it takes a column of jet which is of heavier fluid behind it. So you can see that how nicely this multi-phase interform solver is capturing. at the almost at the same time step for the experimental. So this is the bubble position versus time graph. So these are the experimental results and the commercial software package fluent results, and these are open form results. So we can see the open form, this bit discrepancy is there after a certain time step in the position versus time graph, and that needs to be checked by me more. And but it gives a result like with the it gives a result like accuracy. We can increase it by modifying the solver. By modifying the solver, what things need to be modified, that's we should that I should be exploring it later. So little physics I would talk to about the bubble things here. Like I have run the two cases of simulation of different diameter 5.1 mm and 4.4 mm. Here I see the rupturing things. This is a line diagram. Like by reading the control dict file using the tech plot, it you can do it with the line diagram. I haven't done with the paraform, I have done with the tech plot by reading the control dict file of the open form. So you can see the rupturing things, how beautifully the multi-phase interform solver is capturing. And but the time step is different. Time is different. Time is different actually. For the high diameter bubble, the Reynolds number will be high. That's why it takes less time to disturb the interface as well as in rising uh, information of jet. So here you can see the jet formation and the breaking of jet. So you can see like for the higher diameter bubble, the jet is higher as compared to the lower diameter, and even the breaking time of the jet is higher as compared to the lower breaking time of the jet is lower for the higher diameter bubble. So these are the few streamlines that is for the before rupture, after rupture, and jet formation. But this is the streamlines at different stages. So these are references, and thank you.
Thank you very much. So any question from audience or in the chat? Okay, I have a question. What is the ratio of your density between the bubble and the two sides?
I have run the lower density ratio. Lower density ratio simulation means less than one.
Less than one. And do you have any idea to go beyond it?
Yes, I have to like explore. I haven't checked it for the higher density ratios or with the viscosity ratios. That I need to be checked it.
Okay. And do you could you manage to validate it? In fact, in any other way, not just qualitatively with what you captured with from the experiments.
Uh, Actually, in the experimental paper which I have taken, they have these results only, like qualitative and position versus time graph they have shown. So I thought to first validate this. Later, what things I'll get, I will do for that.
Okay. Thank you very much for your nice talk.
And maybe I can ask a question.
Please, thank you.
This position, thank you for your talk, first of all. Secondly, this position that is measured in experimental work, where is it measured? Middle of the bubble, at the end of the bubble, or at the bottom of the bubble?
Yeah, sir, actually, it's the center of the bubble.
Okay. Thank you.
At the center of the bubble.
Okay, perfect. Thank you.
Okay, thank you, sir.
Okay, I'm the second speaker. Sorry for this. Yeah, this internet connection, and it happens. I'm Ardalan. I will present it, and if he come back he can notify me in a way that we can just switch the first talk and second talk. I'm Ardalan Javadi from Georgia Tech, and the title that I will present is direct simulation of highly bubbly fluids under influence of interfacial mass transfer. In general, actually, we did this work for paper industry. So we replace water with bubbles or foam, let's say foam, to avoid flocculation. But in general, as long as we say bubbly flue, it means that we increase the number of bubbles or air contents in the flue. So you have water, you increase the air content to about 60%. That is still, there is no agreement about this number, 64%. But in general, to give a shadow, it means bubbly flue. In fact, bubbles interact, but not that much. If the air content increases, that will be wet foam. Still, the meniscus is considerable. If meniscus get narrower and narrower, it will be wet foam, and if the meniscus disappears, it will be just single phase air. The point that we continue is with surfactant. We add surfactant for increasing the lifetime of the bubble. In general, surfactant will be added into the flue. It will accumulate on the interface. It will somehow go into the gas side, but we don't care at the moment. In numerical simulation from CFD part, we care about it, but in general from physics side, we don't care about it. In the right, there are different orientation of bubbles and foam and meniscus, which matters a lot in terms of coalescence and stresses or bubble interaction, let's say. What I show you is the implementation of the methodology, and then validation and some real cases Poisson flue. In general, and then I go to remarks. In general, surfactant actually has three major effects. This figure at the bottom is not all from that's from Takagi Matsumoto to 2010 annual review of fluid dynamics. The surfactant in general has three major effects on the bubbles. First, it generates Marangoni stress, Marangoni effect. The surfactant, this is a rising bubble. Imagine a buoyancy-driven flue. The surfactant in general generate a stagnant cap at the top and will accumulate it in the wake of the bubble. So it increases the drag and decreases the terminal velocity. As I said, it increases the lifetime of the bubble, decreases the coalescence, and it decreases the interfacial mass transfer. So any of these effects are particular interest in different industries. In many industries, you have foam and bubbly flues like cosmetics, like oil and petroleum, like water wastewater sludge, and cleaning water, and many others. So they add surfactant, or surfactant is already there with their different reasons. So we add surfactant in paper industry to increase the lifetime of the bubble, to avoid pulp and fiber flocculation.
Hello, sir.
Okay. Great to have you back. I switch. I'm doing the presentation. When I finish, then you can continue from the slide that we lost you. Just keep. You were showing your zero directory and system directory and the contents of your system directory. Since since that point on, we couldn't hear you. So please keep in mind, I will continue that, and please, I give the mic to you. Sorry about it, just internet connection, so we understand it. Don't worry about it. Is it fine? Can you hear me now? Okay. Can audience hear me, or I'm doing a monologue for myself?
Yeah, we can hear you. We can hear you.
Okay, good. Okay, in general, this is for OpenFOAM community, this is trivial. I did two things. That's VOF, algebra. I tried both of algebraic and VOF from OpenFOAM part. This is Interfoam. This is IsoFOAM. Interfoam work with mules because of the reason that you know. So I don't want to go through that. This is just governing equation that I use. The model is proposed by Dieter Both and Holger Marshall, University of Darmstadt, and Dr. Marshall actually kindly provided the code, but the code was not originally, the later version of the code was in OpenFOAM 4. I couldn't use it, so I started writing the code from scratch. This technique, this continuous species transfer model. They worked to propose this model for about a decade. And that's a really great work, but the point
Yes,
is
sir, I'm online.
Okay, great. So I will switch the floor to you. Thank you very much. I will switch the floor later on to you. Thank you very much. This formulation is harmonic diffusion with harmonic diffusion. So it means that the surfactant will go through the bubble in a parallel form. In general, to give an overview of what's going on in this formulation, in the left-hand side is material derivation. In the right-hand side, the first term is a bulk diffusion in bulk flu. The second term is normal to the surface. This normal to the interface. Let's say this is in quotation mark. This gamma F should be defined, but that's not accurate. But keep normal to the surface, and these two terms are parallel to the surface. And this is the formulation of harmonic diffusion to from interface. The point is, if you compile it, basically it doesn't work. That's the matter of numerical schemes. The convective term is discretized using this CIC sum, which is a hybrid numerical scheme. Actually, I managed to use this code from the package that I received from Dr. Marshall from University of Darmstadt. But yeah, the code itself, I couldn't use it. All terms in the right-hand side are discretized with 50% downwind, 50% upwind. And later on, another model proposed, and they mentioned that the downwind scheme should be maximized to receive a better result. The point for all these is that for this model, it keeps the concentration of surfactant inside of the bubble uniform. Later on, other models actually give another way of concentration prediction. So for a basic case, in this case, VOF is not solved, just that PDE that I showed in previous slides solved. So that's a constant, or that's 2D, that's a circle, the circle of surfactant at the center of a circular domain, and gravity is 0. And as you can see, the concentration of the surfactant decreases in time uniformly. Imagine this point here is the interface, and it decreases uniformly and get distributed into the domain with these conditions. Actually, I don't want to go through numerical details because it has lots of numerical details. In general, the resolution at the interface should be fine enough. This is the real case. Right now, VOF is being solved. And the point of this is that we try to validate or compare the result of geometrical view, inter-isoform and interfoam. That PDE finally is coupled with interfoam and inter-isoform. I couldn't compile adaptive mesh with inter-isoform. So adaptive mesh only work with interfoam, so algebraic VOF. And this is a buoyancy-driven flu, rising bubble, reaching terminal velocity, and the concentration of surfactant at the surface of at interface is point of as interface is point of interest, and the effect on surface tension. With interisofoam without adaptive mesh, I stress it, 55 million cells, and with interfoam adaptive mesh, that's about 3.2 million cells. The background mesh is 500,000. With concentration, with some specific values that is needed into the model, and I carefully or conservatively increases the number of layers to resolve the boundary or mass transfer boundary layer at interface. So which is defined by diameter of the bubble divided by Sherwood number. Sherwood number in general is a Nusselt number, but in mass transfer field. So the result in general, the validation is for with this paper 2022, University of Toulouse, France, and in general result at high concentration, C infinity at 1 is very well, and you can see the surface tension. Surface tension is predicted very well. This should be for Wadraner, it should be 70 millinewton divided by meter. Should be about 36 or something, and that's captured very well. Terminal velocity is captured very well, and geometric and algebraic view F correspond very well. But the point is, interisofoam is way more expensive. That's 55 million cells, and you can assume. But for lower concentration, the result is not that good. You see that should be 2.2, but surface concentration, but mole per square meter. Divide. In fact, it distinguishes a lot. The marginal error is huge. So then we continued with maximum concentration or C infinity equal to 1. In a Poisson fluid, again, I don't want to go through all the numerical details. Imagine a pipe, the infinite pipe that we added source them in FV option from OpenFOAM perspective. And here, as long as we are interested only in interfacial mass transfer, not the wake of the fluid, I kept adaptive mesh gets refined, or adaptive mesh refines only the interface, not wake of the fluid, to resolve the interfacial mass transfer as much as possible. And in this case, 15 bubbles. So air content will be something about 2 to 3% of the domain that we get. The size of the domain 1 millimeter and to 1 millimeter. This is the simulation. Please follow the timeline, which is for a very long time. And as I said, for high concentration, it changes the forces on the bubbles. First of all, the most important thing is that bubbles actually offers unphysical coalescence. In our experiment, we don't see, so if you count the number of bubbles here, is not 15, that's less than, that's about 12 or 11, something. So this coalescence is unphysical. It shouldn't give that because of numerical error, because of parasitic currents at interface, and because of the problem that we have with UF. But in general, the bubbles are very closer to the axis. In next slide, I will show the clean case. This is with surfactant. And bubbles survive for very long time. The point is, with Coram number, Weber number, and Marangoni number with different definitions. When we increase the velocity, the pressure gradient increases linearly. So based on the definition, the fluid is still in Newtonian region. This is the point for us. So with 15 bubbles with 2-3% air content, the fluid very much behaves like a Newtonian fluid. In general, we expect, we don't know, nobody knows, that we increase the number of bubbles, how non-Newtonian the fluid will be. So this is the main point of interest for us. This is the clean case, and as you can see, the bubbles are more off axis. Please follow the timeline. The survival time of bubbles are way less. And about the Marangoni stresses, as you can see, the direction of the stress is reversed when the velocity increases. So this is very important point on the survival of the bubble, and actually for capturing the surface velocity of the bubble in general. As I said, when we say coalescence decreases, it means that the surface velocity decreases. So it means that the bubble acts like a solid particle. So that's very important to capture the surface velocity. But in general, as I said, in VOF, actually parasitic velocity at interface causes problem. So my last slide. This is the configuration of stresses. This is the clean case, and the configuration of stresses on the surface, which increases tremendously. This is the distribution of surfactant in the inside of the bubble. The surfactant actually is way off axis, which causes some kind of error in our setup, in our design. That should be considered in our design when we actually gonna put bubbles to avoid flocculation in our cases. In the bottom, this is the distribution. You see the wall shear stress and the stress on the bubble. That's in the same level. So very much the interface acts very much like a solid wall. And in general, the main conclusion here is the faster bubbles travel, the more surface tension decreases. So in this case, when the velocity decreases from 10 centimeters per second to 20, the sigma surface tension decreases from 35 to 31. And when we increase it to other case to way larger, 2 meters per second, here is centimeter per second. 2 meters per second, actually the stress actually increases by 30%, which is a huge effect. So in general, my remarks, the model proposed by our colleagues works very good, it corresponds very well with analytical solution. It works very well for high concentration. In poisson flow, the migration or lateral travel of bubbles is observed, and of course Marangoni stress is observed too. And for algebraic, for any case, it predicts, it offers unphysical coalescence. So in general, I have to acknowledge Swedish Research Center RISE and the US Department of Energy for funding this work, and Exceed and PACE Phonics for providing the computational resources. Thank you, everybody, and let me stop sharing my screen. Okay, if any question, I'm here to answer. Thank you.
Sir, very nice work, first of all.
Thank you. Or
sir,
if in the room, please.
Hello. Sir, like you have done this in the OpenFOAM only, I think. You have done?
Yes.
Okay. So you have modified, sir, interFOAM solver. Since there is two phase, you have modified the interFOAM solver.
True.
Okay. And sir, but the surfactant things, like the surfactant. So surfactant things, sir, like how, like what was your approach to add that surfactant equation, like whether it is soluble or insoluble surfactant equation with this interFOAM solver, like this? I want to like please tell something about this. Like you have added the equation You have added the equation for the transport equation. Like how did you add it? And one more term is there. If you are adding a surfactant things in the momentum equation, one tangential component of gradient term will come. Tangential component. uh Sir, your my voice is coming. Is my voice is audible?
Yes, yes, true. I can hear you well.
Like one tangential gradient term is coming. Like how did you wrote in that, like in the solver, like dal we can write in the open form solver like div as a code pattern in the open form solver. But how did you write that, sir? Gradient term, like tangential gradient term. You can give me ideas like later also, no problem.
Yeah, sure, of course. If I just to give a quick answer, I have to share my screen again. In general, first of all, I refer you to the original paper. They give a very nice discussion about it. Let me share my screen. Can you see my screen? Can you see my
Yes,
screen?
we can see. Yes, we can
Okay,
see.
great.
Yes.
Yeah.
Yes, sir, we
Thank you
can
very
see.
much. Actually, this is the grade. In fact, on the right hand side of the equation, this imagine a gradient of the surfactant. I'm not. In fact, please skip the gradient of our view of stuff. This gamma f is defined as the inner product of face cell and the mesh face normal to the face and normal to the interface. So based on this definition, as long as, in fact, we take our resolution very fine. Based on this definition, as long as the resolution is not aligned with the interface,
Okay.
with this definition, we can consider these two terms are for tangential, that's normal to the surface, and -1. It gives other terms parallel to the surface. So with these two terms, we consider the concentration gradients parallel to the interface.
Okay. Okay. Okay.
Good. If
Thank
I
you, sir.
try
Thank
to
thank
answer it concisely.
Can you
yeah,
hear me?
thank you, sir.
I have a question too. Can you hear me?
Yep. Yes, we can hear
Yes.
you. Thank you very
So
much.
you say you use the 6M solver. Are you using it for both alpha and the concentration, or are you still
Yes.
using it for both for alpha
Yes.
and for the, right?
Yes.
Thank you. My second question is: it looked like your H was always 1 in all your simulation. Was it the case, or did I miss some?
You mean Henry coefficient?
Yeah.
That yes. That is the way that is proposed to calculate the concentration inside. Imagine a bubble. We are talking about UF. Imagine a bubble to close a system of equation. First of all, I forgot to say they neglect. There is no reaction on interface. That's not reactive flow, and they neglect the model neglects the adsorption desorption to from interface. This Henry coefficient is the ratio of concentration at two sides of interface. And this way that you see that H in the denominator is actually the way that they approximate, or the model approximates, the concentration of the surfactant inside of the bubble. Do you see my point?
So no concentration jump.
No, yes.
I think if you don't have a concentration jump, and I don't know if it's something you will add later, you can simplify your CST equation by quite a lot. There is a lot of those terms that disappear if H equal 1. So if this is a condition that will always happen, because obviously if H equal 1, the only thing that really have an impact is the difference of diffusion. So I think every term disappears except for the first one. But of course, if your plan is to look at how H will change, then you need the whole other term. Anyway, there's more comment.
Okay.
Thank you very much for your answer.
Okay, so you mean, thank you for your point. You mean that as long as, you mean I should not take H equals 1?
Well, I mean, this I don't know. This is the surfactant.
Okay.
There is a physical reason to take H equal 1. I'm meaning that if H equal 1, I think the model you're using is more advanced and you don't need all of those additional terms. If you look at the equation, you will see that
I see.
Most of the terms disappear actually as H equal 1. But if in the future,
yeah, that's a very good point.
If in the future you plan to have a look at the impact of changing H, then of course this is right. Anyway, thank you for your answer.
Yeah, thank you very much. That's a very good point to mention. Actually, I see your point because actually H equal 1 in general should be unphysical, because the concentration of surfactant at both sides of interface should not be equal. So that's very good point. That's something that I should look into. Thank you. Okay, the third speaker is Milad Bagheri from PhD student at Technical University of Darmstadt, a unified finite volume framework for phase field simulation of arbitrary number of immiscible, incompressible flues. Yes, please go ahead. Thank you.
Yes, hello everyone to both online and on site. So I will just turn off my video to see the presentation. Okay, perfect. Yes, my name is Milad Bagheri. I'm a PhD researcher in the computational multiphase flow group at the Technical University of Darmstadt. The group is led by Dr. Holger Marshall. And I'm working in Collaborative Research Center 150, and this work is in collaboration with Dr. Abdurrahman Dadvan from Urumi University of Technology and Dr. Martin Warner from Karlsruhe Institute of Technology. So here are the contents of my talk. I will start with the motivation, and so basically, why do we need to extend our solver to be able to perform more than 2 phases? And what are the challenges in the extension of the solver? What has been done so far with us? So we had a 2-phase flow solver, phase field diffuse interface solver, which we extended it to cover n phases. And basically, I will talk about the diffuse interface library that we developed, and a lot of simulation results and some concluding remarks by the end. So a bit of motivation, why more than 2 phases in the computational domain. In the collaborative research center that I'm in, we are considering 2 industrial examples. One of them is an internal combustion engine. If we consider an internal combustion engine and we focus on an individual cylinder, we can see that during the intake stroke, where the fuel is actually sprayed inside the combustion region, this fuel is atomized into tiny droplets of high speed, and this tiny high speed droplet will collide with the lubricating oil film that is on the wall of this piston. Now, this may cause transport of the oil droplets from the wall of the piston inside the combustion region, or it may cause the weakening of or change of the transport properties of this lubricating oil film here. So this is one application. The second application that we look at is in the exhaust gas after treatment, where the urea water solution, or what is commonly known as AdBlue, is sprayed in the exhaust gas. We can see that we are having, after this is the mixer, so after the mixer we are having a lot of droplet and film deposition, which is there is a deposit film here, and again we are having somehow droplets and film interaction here. So we are looking at basically a sprays applications and what's going on. So these processes are not really well understood, and this is what this collaborative research center is about. So this very complicated process is simplified into a normal drop impact process where we have a diameter, where we have a droplet of certain diameter and certain velocity impacting a film of certain thickness. Now, we can have the case that the droplet and the liquid film are of the same liquid, or we can have the case that the droplet and the liquid film are of different liquids, which means that in this case, we need to account for the effects of miscibility and immiscibility of the liquids. Now, these experiments were conducted at TU Darmstadt by my colleague Bastian Stumpf. We can see different scenarios of the droplet impact, normal droplet impact. These are the cases where we have the drop and the liquid film of the same fluids. We can see that we have deposition, crown formation without a splash, and we have crown formation without a splash also, but with generation of a central jet, and we have crown formation with a splash with generation of secondary droplets and a lot of chaotic physics that are happening here. So clearly we are dealing with a multi-scale physics. Now, if we have, for immiscible liquids, we have oil, drop impact of oil onto water, and for miscible, we have water on water. For these two experiments, all the parameters such as the diameter, velocity, and thickness of the film are the same, but obviously we are having the effect of immiscibility and miscibility. This is the case of immiscible fluids, where we have secondary droplets, which we are interested in the composition of them, that are containing basically both of the phases. And in the case of miscible liquids, we are having the effect of miscibility is very clear. Mixing is already happening, and we are having secondary droplets generated, which is basically the physics that we are trying to capture. So these processes, we perform numerical simulation with our two-phase code with these on the left-hand column videos successfully. Now we are here, basically immiscible liquids, and we are about to extend to simulation of miscible liquids for high-speed drop impacts. Impact scenarios, and we have a central jet which is basically mixing is also happening inside it. So in order to capture these processes, we use phase fill method. There were a couple of talks yesterday about phase fill methods, but in terms of material science. We are talking about basically fluid dynamics, and we use phase fill method. In the phase fill method, the interface is treated as a thin transition layer of finite and prescribed bit. And I placed a photo of a sharp versus diffuse interface where the concentration profile changes from one phase to the other. We can see we have a discontinuity at the interface for sharp interface methods, such as volume of fluid. But for diffuse interface methods, we have a rapid but a smooth transition of concentration from one phase to the other. This is actually a tangent hyperbolic profile. And what are the challenges? Well, we have to initialize this tangent hyperbolic profile in terms of we have to have a proper initialization of the fields. Not only that, we have to maintain this profile during the course of the simulation. We are dealing with a fourth order PDE, which brings numerical complications. And due to this nature of interface, we are having extra model parameters that one would normally not see in diffuse in sharp interface methods. Most importantly, we need to resolve the interface with sufficient resolution. In order to do that, we use adaptive mesh refinement. This is an example of how an interface is resolved with the use of adaptive mesh refinement. And what are the challenges? So these are the two-phase scenarios illustrated, but what are the challenges to extend the code to cover n phases are mostly about consistency conditions. We need the model to be reduction consistent, which means that the n phase model should basically reduce to the two-phase model, and thermodynamic consistencies such as mass, momentum, and mass and momentum conservation, and the model should honor second law of thermodynamics. So what has been done so far? These were the three experiments that I illustrated, and these are the comparison of the numerical simulations. We can see on the right-hand side of it, the adaptive mesh refinement in action, and on the left-hand side of it, we can see the velocity, the interface that is colored with the velocity magnitude. We performed these numerical simulations, and we had very interesting findings that for high dynamic cases, we need to account for interfacial relaxation. which means that we need to take into account a non-equilibrium effects, which led us to publication of this paper. We did not only do a qualitative, but we did quantitative comparison of the height of this crown that is forming. We also varied the number of cells across the interface to see the effects, and we also measured other parameters such as the base diameter, rim diameter, and etc. Quantitatively, and compared it with the experiment. We were also interested in explaining the process of kinematic discontinuity with the help of velocity vectors, which is illustrated here, and one can refer to the paper to read more about it. Now, we were also interested into the process that basically generates this secondary droplets. So we perform high-speed two-phase droplet impact process in 3D. Here, the Reynolds number is more than 1,000. So we were interested to study the impact morphology. This is the simulation setup, where we have generation of the crown, and when we have rim formation and instabilities. This rim formation and instabilities lead to generation of these fingers, and these fingers fragment into secondary droplets. Here we can see that we are dealing basically with all sizes and types of droplets, and droplet shapes, which helps us to capture them with the use of adaptive mesh refinement that we are using in TU Darmstadt. So this is an ongoing work still, but it's very promising at the beginning, now even. So as I mentioned, we use phase film method. This is a diffuse interface model. In order to model interface dynamics, meaning evolution, dissolution, or even creation of interfaces, we use the Cahn-Hilliard equation, which is here. And in order to model hydrodynamics, we couple it to the Navier-Stokes equation using this coupling term, which is shown here. Here, I put a sample of the sharp interface transport equation of the volume of fluid, let's say, model, of course, without mass transfer or phase change or etc. We can see on the right-hand side of the transport equation, we have 0, but for the two-phase Cahn-Hilliard equation, there is on the right-hand side, a physical right-hand side is appearing. These are the parameters that appear as a result of having a diffuse interface. We are having a mobility scaling parameter. We are having a chemical potential, which is a function of basically we are having a double well functional. This double well functional basically determines where my bulk phases are, basically separates the phases from each other. So the roots of this is -1 and 1. So I have one bulk phase at -1 and one bulk at 1. We have the mixing energy, which is basically the interfacial energy at the interface. Now, the story of where these terms are coming from, there are a lot of paper about them, but the main paper, the best one is the Cahn-Hilliard, which started basically this work. And yeah, it is basically coming from the concept of free energy of a system. So if a system of a non-uniform composition, if you describe the system, the free energy of a system of non-uniform composition, and we take the variational derivative of the total free energy of a system with respect to its composition, we arrive at a composition, at the chemical potential, which models kinetics or evolution of the system. And the work that basically Cahn and Hilliard did, that they said that the free energy of a system is not only a function of concentration, but also the concentration gradient. And this concentration gradient will then basically contribute to the interfacial energy related effects. Now, after computing the Cahn-Hilliard equation, we need to couple it to the Navier-Stokes equation. This is the coupling term, which models capillarity of the diffusive interfaces on the basis of Korteweg stress tensor. Now, this system of two-phase equation, which you saw the simulations in the previous slides were extended to cover n phases. This is actually based on a very recent paper from Purdue University, where they proposed fully reduction consistent and thermodynamic consistent system of equations. Now we need to consider a scaling law for the mobility parameter between each pair of the phases. We need to compute, obviously, the chemical potential for each single phase, and we need to consider the mixing energy between each pair of the phases. Obviously, the coupling term should also consider the effect of all the phases. Now, a bit about the software structure. We developed it in FOAM Extend 4.0, 4.1. The top level solver is named phase-fill foam, and it is designed in a way that the software extensibility is guaranteed, so many models can be added. And since we are dealing with a fourth order partial differential equation, we split it into two second order partial differential equations, and we solve them at the moment using segregated method, one after the other. This is a class structure basically with all the subclasses. The main one is multi-phase systems, which covers basically the models that can be added for each of the parameters that were explained in the previous slide. And we can have, we are currently working in the with the Cahn-Hilliard equation, and we are solving it in a segregated manner. Now, the end phase model was created and should obviously be tested. We did a lot of end phase, basically more than three phase tests with this model to see how it works. The first case is the floating liquid lens problem. This is a benchmark three-phase problem that is quite famous in the literature. We have a liquid oil drop that is floating on the air and water interface. Now, and we change the magnitude of the gravitational acceleration, and depending of the magnitude of the gravitational acceleration, we are having different elongation. So here is the start of the simulation for all the three cases. We can see depending on the magnitude of the gravity, we are having different basically elongation, and we have different. So what we measure is basically this thickness of the puddle at the middle, and there is an exact solution for the gravitational acceleration of 0, which matches very well, and for other gravities there's an asymptotic solution which compares or results basically compares very well with the exact and asymptotic solution. So we moved on. We saw some bubble rise simulations. Now this is a rising bubble in two stratified layers. So again, the idea is the same. We have a bubble. The bubble tries to rise from a heavy fluid and faces an interface and goes to a light fluid. There are two expected outcomes. The bubble is either penetrates or stay entrapped at the interface. Now there is a criteria based on a critical volume that says if the volume of the bubble is more than that, it will penetrate this interface, and if it's less, it will remain trapped. We perform simulation at different bubble ratios, as you can see here. So from left to right, the bubble ratios is increasing, and we can see this is a running time of the simulation. Obviously, we can see that the bubble basically remains entrapped for the bubble ratio less than 1. The bubbles basically breaks the interface and moves to the lighter fluid, and basically it has trailing of the heavy fluid with it carries a trailing fluid of the heavy fluid with itself. This is also compared quantitatively using this formulation, and also qualitatively with the literature. Now we have rising bubble in 3 stratified layers. So this is the same idea, but now we have 4 phases. So we have a bubble that now we are having basically heavy and let's say light fluid. So the bubble should basically cross these interfaces for this scenario that is coming from this end phase paper. Here we just follow the trajectory of the bubble. We can see that with showing the velocity vectors and magnitude of velocity at the bubble surface, we can see that the bubble crosses the first interface, and then it crosses the second interface and moves to the top of the computational domain, which then stops there. Now, these results were also well, there is no experiments for this case, obviously, but were compared qualitatively with the paper, and similar results were obtained in both works, in ours and the paper mentioned here. So this is another benchmark case. This is a 4-phase problem, dynamics of 4 immiscible and compressible fluids. We divide the computational domain into an air side and a water side. In the air side, we have an arbitrary fluid, F2, and which we have gravitational effects here in the air side. And in the water side, we are having an air bubble, and we are having an arbitrary fluid, F1. So we have buoyancy effects basically dominate the lower part, and gravitational effects dominate the upper part. This is the left and right are periodic boundary conditions, and this is where when the simulation starts, we are having, due to buoyancy, the bubble rises. This F1 fluid rises slowly, and obviously F2 fluid falls into the interface. And we are also having a small entrapment of air. Obviously, we are having a 2D computational domain, so basically there is no time for escape for the air. These results were also compared. Obviously, there is no experiment for this work. It's, in general, for 4 or 5 phases, there are very few numerical works, or I'm not even sure if there are any experiments. So this results compared also very well with the literature. Qualitatively with the literature. Now we talked about droplet impact scenarios. So we set up a 3-phase drop impact scenarios. We did the experiments at TU Darmstadt. So we have an oil. This is an axisymmetric setup. So the process remains axisymmetric. We have an oil drop of diameter 1.44 millimeter, which impacts a water film of diameter 0.5 millimeter. The velocity of this impact is 2 meters per second. And we have seen very few or close to zero, basically, numerical simulation of this nature. This is the result of the simulation in basically fancy ray tracing post-processing. We can see the surface phase generated, the crown is generated, and etc. all the other effects. Now, but how are we compared to the experiment? We haven't done quantitative experiments for this case, just the qualitative as of now. So we can see that compared to the experiments, we are also very good. I have to mention that the water is dyed with fusion. Fusion basically keeps the transport properties of the water intact. It doesn't change them a lot. We can see we have a very good comparison at the beginning of the simulation. Toward the end, for the dome-like structure, we are having a bit of differences, but overall it's a very good comparison. And this work was actually published yesterday. And yeah, so this is the concluding remarks. We have implemented the method to cover more than 2 phases, and it works quite well. We showed lots of validation case for 3 phases, and we showed the potential of the method for 4 phases. The next in our to-do list is to develop predictive approach to partial miscibility in non-dilute mixtures, and basically work on 3D impact simulations. And we are also working on dynamic load balancing technique. My colleague, Mohammed Alvardi, presented this work yesterday. And yeah, last but not least, I would like to thank German Research Foundation for founding this project. And yeah, I'm happy to answer if there are any questions.
Thank you very much for a very nice talk. And congratulations about your new publication. Okay, any question from audience?
Yeah, I have a question. I was somehow puzzled by your second double well potential, C square, C plus 2 square, I think. Can you explain what that term is doing? Yeah, we can't see it. It's on the right.
Okay, yeah. So this, well, the best way is to refer you to the paper that this work is coming about. But this is the way that basically makes the model reduction consistent and thermodynamically consistent, and basically separates the 2 phases together from each other.
Okay, I'll look at the papers and thank you.
I can see there are some simulation. There are some, questions in the chat. The last one is why not use WOF? Well, we would like to move toward miscible simulations, and for performing miscibility, we need a lot of physics, a lot of natural physics is happening at the interface. And in volume of fluid simulations of this type, normally you add an arbitrary diffusion term on the right-hand side, but we want it to be predictive physics-based. So this should be an interfacial region. There should be there so that we can work with it. The other question is that in Cahn-Hilliard equation, is the phase of the fluid conservative quantity? The answer is yes. I saw in your high impact simulation some of the second droplet vanish. Yes, some of them not vanish completely. Actually, some of them change shape to smaller droplets and at different time scales. Because the camera is 17,000 frames per second, 37,000 frames per second, and some of the drop maybe we don't see basically the change of the shapes of the droplets, yes, there might be some volume loss based on our last measurement. I think it is below 1% of volume loss, which is very good, I believe.
Hello.
Yes, sir. Sir, the camera which you have used for your experiment, that is of how much frame per second, and do you think minimum frame per second, how much it requires to capture the shape of the bubble or droplets?
So yeah, as I mentioned, it's depends on the simulation, depends on what features you would like to capture, and depends also on the speed, Weber number, Reynolds number, and etc. But we have two cameras set up, but one is 20,000 frames per second and one is 37,000 frames per second, depending on what you would like to capture.
Okay, and sir, can you tell the way from the, obviously when you are inserting a bubble from the bottom, like how you are inserting a bubble, what setup can you tell by speak about the setup, like how you have inserted a bubble inside the beaker?
So you mean how this bubble is here, right?
Yes, what bottom you have done at the bottom of the beaker, what you have done, or container?
Swag for form. We use swag for form to initialize the tangent hyperbolic profile, and basically you initialize this and you subtract a bubble from it. So this is done with using swag for form.
Okay. Thank you, sir.
I cannot hear if someone is talking, I think.
Excuse me. Hi, Milad, great presentation. I have a very technical question. If you can go to the second to last slide.
Second to last, this?
Yes. What is the software that you use to visualize the droplets, because it looks great? The left one.
Thank you. Yeah, ParaView ray tracing.
ParaView ray tracing looks like that, just default ParaView ray tracing.
Not default. You need to how to say that, you need to play a bit with the lighting features of ParaView there, and basically the way that the colors are presented. If you play a bit with them, and you can get what you really need. But this is how it looks like.
Okay, great. Looks great. Thank you very much.
Thank you.